Hello, my name is Peter Amstutz. I am the CTO of Curie, a longtime developer on the Arvados project, and one of the co-founders of the Common Workflow Language project. Today, I'm going to present a framework for understanding how to design biomedical data processing pipelines and the features of Arvados that enable you at every step. If you're listening to this talk, you probably have a scientific or clinical data processing problem and have heard that Arvados might help you build a solution, but you're not quite sure where to start. As a couple of examples, maybe you have FASTQ files from a DNA sequencer and want VCFs, or maybe you have a large number of images and need to do feature detection. You might be comparing Arvados to other products or trying to decide if you need to build something yourself. You might have regulatory obligations to keep track of where data came from or how a result was produced. You're probably working on a scale where you have hundreds or thousands or millions of data sets that are completely unwieldy without automated, repeatable, reliable processes. Arvados supports every step of the data processing process, so it can be used as a full stack for new projects, but also features a variety of ways to integrate with existing systems so you can pick and choose the best solutions for your particular problem. The data lifecycle begins with data collection. In the biomedical space, some examples are scientific instruments such as DNA sequencers, digital microscopes, mass spectrometers, or could include patient records, medical monitoring systems, or other data sources. Once data is collected, we need to bring that data from the point of collection and ingest it into the system where we're actually going to do the work of processing it. We need an organization system so we can keep track of how it relates to other entities, such as the patient it was collected from or the study it was collected for. Next, we have the actual data processing, where the real work happens of transforming the data set into a result. Finally, the result has to be published so that scientists or clinicians can consume the result and use it to make clinical decisions or perform further ad hoc analysis. At the bottom, tying all the steps together, is orchestration, which is overall management of the data lifecycle and rules for moving from one step to the next. Thinking about ingestion, organization, processing, publishing, and orchestration gives you a framework to understand what questions you need to ask and answer in order to design your solution. Of course, you also need to think about data collection at the beginning and data consumption at the end, but these are inherently domain specific. I want to stress that these steps always exist, but if you don't have documented processes and systems that keep records about what was done, you'll end up with these steps carried out in an ad hoc fashion by someone typing into a command prompt who might not even remember what they did a week later. For those who are less familiar with Arvados, here is a very quick introduction. Arvados is an open source platform that combines both data management and workflow management capabilities at scale. We call our data management system Keep and our compute management system Crunch. Arvados helps you organize data at petabyte scale and analyze it with reproducible computational workflows. Arvados runs on public cloud providers and on-premise infrastructure. Arvados is a set of services, APIs, command line tools, and web applications that enable you to store data, run workflows on that data, and share results with others. Now let's dig into the steps of the data lifecycle and talk concretely about what is involved and some of the things you need to think about. The first thing you need to know is what your data actually is. At the lowest level, it's probably a bunch of files and directories. You'll also have metadata about how the data set was collected. Metadata might be stored in a file that is part of the data set, or you might need to query it from a database or API. If you're building a greenfield solution with Arvados, you want to minimize extra data handling steps and upload the data directly to Arvados from the data collection source. Although If the source is a locked-down scientific instrument, you may need to move the data to another system on the local area network, which will upload to Arvados. On the other hand, if you are integrating Arvados into an existing solution, you may already have your files stored in another location, in which case you may want Arvados to download the data when it needs to use it. For the upload case, consider writing a script that monitors to see if data is ready, then uses the Arvados CLI tools or SDK to create an Arvados collection and upload the files to that collection. If the data is many gigabytes and the data collection process takes hours or days, you can save a lot of time by uploading data incrementally as it is produced, instead of waiting to the end and then having to transfer several hundreds of gigabytes. The arvput command keeps a record of which files it has already uploaded to a particular collection. If you run arvput with the update collection flag, it will determine which files are new or have changed and upload only those files. You can run this command repeatedly to upload files as they are being generated, so that when data generation is finished, most of the data is already in Arvados. For another approach, if your system is capable of writing to an S3 bucket, Arvados provides an S3 compatible API as another means of uploading data to a collection. If your data is already present in another storage system, such as an S3 bucket, then you might prefer to initiate the data download when you need it. Arvados will download HTTP URLs automatically when used as workflow inputs, which is convenient with public data sets and time-limited authorization schemes such as S3 signed URLs. Another, more flexible option is to put a download step in your data processing workflow. You can use any downloading tool with any data transfer protocol and provide credentials securely using the Arvados extension to support secret inputs. If you have a very large amount of data, you could even use a workflow scatter to perform downloads across multiple machines to increase throughput. Now that you have some idea of what your data is and some strategies for getting it into Arvados, how do you decide where the data is going so you can easily keep track of what is happening and be able to find it again? Arvados has two main units of data organization. A collection holds files and directories. A project holds collections and other projects. A single Arvados collection can scale to millions of files and terabytes of data. Collections and projects have searchable metadata properties. As part of your data ingestion process, it's a good idea to extract metadata from the upstream system and set properties on the Arvados collections and projects you create to keep track of where data came from. Properties also allow you to search and filter collections and projects. To ensure good data hygiene, you can define a metadata vocabulary, and Arvados will enforce that only values in that vocabulary can be used. This is how a collection is displayed in Arvados Workbench. Collections have several identifiers, including a name, a universally unique ID or UUID, and portable data hash, which is an immutable content address for files in the collection. If two collections have the same portable data hash, then you can be confident that they contain exactly the same data. Arvados tracks collection versions. The database UUID always points to the most recent version of the collection. Here, you can also see metadata about the collection, such as where the data was collected, the file format, and species of data. And then at the bottom of the screenshot, the list of files in the collection, which you can click on to view or download. The typical unit of sharing and organization in Arvados is a project. You want to choose a system that makes sense for your institution. In a research setting, you might create an Arvados project for each study. In a clinical setting, you might create an Arvados project for each patient. Use metadata describing the subject to make it easier to find in the future. When choosing how to organize data in collections, you probably want them to correspond to logical batches of data, such as a single instrument run. This makes it easier to record meaningful metadata. In particular, once a collection has been used in downstream processing, it's a good idea not to change it. Although Arvados tracks collection versions and processing history will correctly refer to the version that was actually used, it's still easy to get confused. Now that you have your data sets loaded into the system, you need to implement the actual data analysis. Running analysis and getting results is what we're here for. What data processing do you actually need to do? The basic building block of data analysis is a program which runs with some command line parameters, reads input files, executes the desired algorithm, and produces output files. This can be your own custom code or an off-the-shelf tool. If you need to string together multiple tools, you need a workflow. Arvados supports a Common Workflow Language, or CWL, for describing workflows. CWL is a specialized programming language for describing how to turn parameters into a command that runs in a Docker container, how to collect results from the command, how results flow between steps, and what steps can run in parallel. CWL is a standard with multiple implementations, so you may even already have CWL workflows that you want to bring to Arvados. Because CWL is designed to be portable, CWL workflows developed for other platforms will run on Arvados with few or no changes. We offer a hands-on training module for CWL on the Arvados documentation site, and you can find more general CWL resources on commonwl.org. The compute management component, Crunch, handles the nuts and bolts of launching programs. Arvados ensures that appropriate compute resources are available to execute each step of the analysis, provides read-only, on-demand access to files in Keep using a file system mount similar to NFS, automatically restarts failed jobs, and can recognize when a compute task has been done before and reuse the previous result instead of rerunning potentially expensive tasks. Although CWL is portable, Arvados provides a number of extensions to help you take advantage of Arvados features. You can supply these as workflow hints, and they will be ignored by other CWL runners that don't support them. The process properties and output collection properties hints let you set custom metadata on the workflow run and on output collections. The intermediate output extension tells Arvados to automatically delete intermediate results after a period of time to avoid retaining intermediate results indefinitely. Using CUDA requirement, you can request compute nodes with NVIDIA GPUs. When you are running data analysis at large scale, optimizing for cost and runtime become very important. The Run in Single Container feature lets you specify that a sub-workflow should run in a single container on a single compute node. This is beneficial when you need to run a sequence of short steps with similar resource requirements by avoiding the overhead of launching a separate container for each step. Spot instances can provide significant cost savings by using excess cloud capacity at cheaper rates, but come with the risk that they may be reclaimed by the cloud provider before your job is finished. The Use Preemptible hint lets you control which parts of the workflow should or should not run on spot instances. Arvados collects extensive metrics from compute jobs to help you understand what compute resources you actually need to use, so you can make sure you're running your jobs on the cheapest instance type that will do the job. Use CrunchStat Summary tool to graph these metrics to understand the usage of resources over the runtime of a job. Once analysis on a dataset is complete, you will have results in the form of plots, graphs, reports, tables, variant call files, or anything else in the analysis output collection. How are you going to make that data available to the end user who will ultimately consume it? Arvados provides a variety of data access options. In many cases, users can view results directly in Workbench or use Workbench to download to their local desktop. Other options include using the WebDAV feature to access the contents of a collection as a network folder, mount the collection at the Linux command line using arvmount, download files using the CLI tool arvget, or use the Arvados S3 API support to access the collection as if it were an S3 bucket. Instead of downloading from Arvados, you may want your analysis workflow to push the data to another system when it is completed. This is the inverse operation to data ingestion, but the strategy is similar. Use a workflow step to execute a data transfer tool with the files you need to upload as input. Arvados secret handling lets you provide credentials necessary to access protected resources. Finally, you need to think about how all the different pieces will fit together. Orchestration is about defining the rules for coordinating between the steps of the data processing lifecycle and with the rest of the world. Orchestration is almost always specific to the particular task at hand and your own organization's business processes and systems. This might be basically manual. An operator checks to see that data collection is completed, so they click a button to upload the data. Then later on, they check to see if the data upload is completed and click another button to launch the workflow, and so forth. However, if you can, you probably want to automate this by writing scripts. One approach is a custom launcher script run by the user, which manages the ingestion and organization steps according to your chosen data organization scheme. Another approach is to write a service that checks for conditions in Arvados or other systems and then performs actions when those conditions are met. This can be as simple as a Python program running in a loop that performs an Arvados API query once a minute. A useful technique is to store your orchestration state in Arvados metadata properties on the collections or projects that are under consideration. For example, after data ingestion, but before starting data processing, you may require some additional validation or review, which can be tracked by adding a needs validation or past validation status. Any operation that can be done manually through Workbench or a command line tool that you might want to automate can be done in a script using the Arvados API. Sometimes, when integrating with other systems, it may make sense to put the other system in the driver's seat. In this model, the user interacts with some external application, and then that application tells Arvados what to do. If your data publishing process exports results out from Arvados to another system, the end user might never need to interact with Arvados directly. Time to wrap up. I hope this has been helpful. I have presented a framework identifying 4 basic steps that are universal to large-scale data processing tasks: ingestion, organization, processing, and publishing, and described a variety of options that Arvados gives you to efficiently and effectively implement these steps. I have also highlighted the role of orchestration for both technical automation and the way of describing the business processes that tie these steps together. Finally, I argue that Arvados, by combining both data management and compute management capabilities, provides essential value by enabling you to track your entire data lifecycle, which single-purpose workflow management or data management systems cannot. Thank you, and I'm now available for questions.